Hello again. You get me again. So we're going to continue with our lectures on network programming by looking at some formal reasoning techniques. Just to put this in context again, so we last time looked at the design of this netcat language, which is a higher level language for network programming based on clean algebra with tests, and we formalized the denotational semantics. Two quick things. I posted some notes and put the link on Piazza. I've been fixing small typos that I've noticed as I give the lectures and that some of you noticed. So if you saw something that was confusing, it's possible that there was a small typo. I think I fixed 3 by now. And I put those on the web page. I also want to correct one thing I said. In my little sermon on denotational semantics, I implied that things like evaluation order don't necessarily need to be committed to in denotational models, and that's not quite right. What I should have said is that various sort of aspects of how you formalize an operational semantics can sometimes be ad hoc, but the same kinds of issues about evaluation order do arise in the denotational setting as well. Okay, so let's dive in and talk about reasoning. The kind of high-level motivation for this is that networks have become very important, critical parts of our infrastructure, and although for the most part, networks work pretty well, there are a number of these sort of high-profile outages that are in the news sort of every few months. These are actually a bit old. But what's I think noteworthy about these is that these are not sort of fly-by-night, small companies that aren't technically sophisticated. It's not like startups that don't have good people. These are some of the biggest tech companies in the world, and ones that presumably would put a lot of resources into making their networks reliable. And yet, they keep having these bugs that arise that take down their whole service. So GitHub has had a number of outages, and if you go read their sort of postmortems on these things, very often it's due to things like a misconfigured router or switch that caused, in this case, a loop in the network. Or Amazon had this big outage in April of, I think, 2012, where they were trying to do some relatively routine maintenance, and they made a configuration change that caused a backup network to get swamped, which caused a bunch of machines to start spending more traffic, which took down yet a different network, and sort of this sequence of cascading failures that actually took down one of their data centers and all of the cloud-hosted services that were there for a few days. GoDaddy had a service outage, also due to some internal network events. They didn't exactly say what those were. And my favorite is, I think this is also 2013, United Airlines had a network connectivity issue that led them to actually have a full ground stop at some of their hubs, including San Francisco. So, when the network breaks, it's really, really, really bad. And I don't want to imply that the people who run networks are somehow not sophisticated people. They're actually some of the best engineers I've met are people at companies like these, or I spend a lot of time talking to the Cornell networking folks, and these people are incredibly careful, incredibly talented and smart engineers. But the problem is that they have really bad tools. Essentially, the approach is to sort of be very familiar with the low-level languages that routers, switches, firewalls understand, and then to use sort of decades-old rudimentary tools like ping and traceroute to try to figure out what's going on when you have some kind of error. So it's all, they've sort of developed lots of best practices and they have lots of special domain knowledge, but they don't have good ways of systematically and automatically checking properties of the network. So the alternative that I and many other people have been advocating for over the last few years is if we have software-defined networking architectures and we have programs that specify what the network is supposed to do, maybe we should use the kinds of techniques that we use with software in general, things like type checking or testing or even verification, to check that certain critical invariants hold all the time. So the idea is, we want to somehow take the network in a current state, encode it in some kind of high-level language or other framework, and then verify important invariants like, does the network provide connectivity to all the hosts that are connected to it? Or is it free of loops? If you have a forwarding loop, that's a really bad thing in a network because it means that packets are cycling around and around and around, at least until their time to live counter goes to 0, but sort of consuming bandwidth and using resources, and they can cause other legitimate traffic to be dropped. So we'd like to build tools that can check these automatically. And in fact, not so much in the PL community, but actually in the networking community, starting about 5 or 10 years ago, there was sort of a resurge of interest in formal methods. I should say I don't want to claim this is somehow a new trend. There's a long history of using formal methods in networking that goes back decades. But I guess about 2010, people started realizing that with these SDNs that you could take descriptions of the intended configuration of the network and start systematically checking properties of it. So some of the earliest work is a system called Flow Checker out of, I think, North Carolina, a system called Anteater out of UIUC, a testing tool called NICE out of Princeton and EPFL, header space analysis out of Stanford, that was one of the high-profile systems, and Veriflow, again, out of UIUC. So all of these tools either do some kind of systematic testing of network behavior or even verification of certain kinds of properties. I think this is really exciting. This is not what sometimes happens where a bunch of PL folks get together and say, we should build, verified software systems. I think that's a good thing to do, but this is being driven really by people from the networking community and even by practitioners. And there's now a number of startups. Veriflow, for example, has become a startup, and they're finding lots of interest from people in industry in this kind of technology. Just to say a few words about how these systems work. Most of these systems work by somehow translating network configurations into input problems for existing solvers. SAT solvers or SMT solvers have gotten really fast, and some of these systems are sort of essentially clever front ends that take in a network configuration and then maybe do some munging of it and then spit out maybe a SAT instance. And then if the SAT solver says the instance is satisfiable, that tells you something about the network. There's also a few systems that have actually developed novel data structures and decision procedures. So header space analysis, for example, is based on a sort of geometric interpretation of packet processing functions. And they have a bunch of really clever representations and data structures that let them encode the configuration of an entire network very compactly and then check properties of that representation efficiently. So it's kind of it's a fun area, and it's still ongoing. A lot of these tools and the stuff I'll talk about today is limited in certain ways. So there are lots and lots of properties you could want to check of a network, including maybe at the lowest level what most of these tools do, which is for a static configuration of the network, what reachability properties do you have? Or to put it another way, if I put packets at one place in the network, where is that packet going to go? So this is arguably important because it's sort of the essential function of a network is to move packets around. And again, things like, does the network provide connectivity? Does it isolate certain regions of the network from each other? And is it free of loops? All of these can be expressed as reachability properties. But there are other properties that you might care about. So just to identify some of the major dimensions that are sort of currently being explored or haven't been explored yet. One way you could go is you could make the notion of what a configuration is more expressive. So as we saw, OpenFlow and Netcat and a lot of these existing formalisms are essentially stateless. So every packet is treated, is processed separately from every other packet, and there's no state that causes there to be any dependencies between packet processing. And of course, there are devices in a network that are not stateless. So anything that's called a middle box or even certain kinds of router and firewall functionality sometimes involves state. And so one direction you could push, and there's a group at Berkeley, along with several other places that are pushing in this direction, is to try to make these decision procedures more powerful so that they can represent not just static snapshots, but encode the behavior of devices that collect and depend on state. Another direction you could go is, in a sense what's going on is, if you remember the picture from this morning, if you have a sort of control program that's generating a sequence of static configurations, what the existing tools and Netcat verification does is it takes each of those snapshots and dynamically checks if it has some properties. So it's kind of like, if you want to think of like runtime type checking, it's kind of like dynamic type checking. You might wonder, like, could we somehow instead verify the control program that's generating those configurations? And maybe we could prove some properties of the control program and not have to bother with this dynamic verification, which might be expensive and doesn't catch the bugs until it's maybe too late. So there's also people who have been working on that dimension. Todd Milstein at UCLA and some folks at MSR have been building tools that can systematically explore the state space of a rich control program, maybe a routing protocol, and check that it never exhibits some bad properties. And then there's another dimension that you could go that I think is exciting because I'm currently working on it, which is a lot of these systems are deterministic in nature, but there's a lot of uncertainty in a network. There's uncertainty about what kind of traffic will arrive at the edge of the network, and there's also uncertainty about what kinds of failures will occur, and there's also uncertainty about sort of exactly how packets will be processed. So a lot of networks use randomization internally. If you've heard of a protocol like ECMP, they basically pick random paths to try to spread the load over the network. And so if you want to model that kind of behavior, then your semantics needs to not be some kind of deterministic functions, it should be probabilistic functions. So a bunch of us at Cornell have been working on probabilistic extensions of Netcat to let us formulate and check properties of these more complicated networks also automatically. Okay, but today we're going to stick with the simplest level, which is static verification of data planes. Just to review Netcat syntax, we went over this morning. So it's this language you get when you combine Boolean expressions with clean algebra or regular expressions and packet primitives. And one small difference that I had highlighted at the beginning, I'm going to rewrite the link primitive in terms of a more basic operator called dupe. So I like presenting Netcat with the link operator because I think it's a little more intuitive. But in the context of verification, it's more convenient to work with a slightly less powerful operator. So the idea with dupe is dupe just captures the duplicating functionality of the link operator we saw before. So dupe is going to basically make a fresh copy of the head packet in the history. And we'll see it in just a second, the semantics. And we can get the behavior we had before of links by a simple translation. So the link from S to S prime becomes match on things at S, duplicate the packet at that point, and then rewrite the switch to be S prime. So dupe is in some sense more primitive because it doesn't by itself involve any filtering or modification operations. One other thing that I'll use today in a few places is it's often convenient to take a Netcat program that involves dupe in many places and somehow forget about the paths that program describes and just think about the input-output behavior. And we can get that by, if we just go replace every occurrence of dupe with true, just do a simple syntactic substitution, then you end up with a term that doesn't contain any dupes. And so you can quickly convince yourself that any packet, any history that you feed in will have exactly the same length for all the outputs. Sorry, all the outputs that come out will have the same length as the input. So in particular, if you feed in a singleton history, you'll always get out a set of singleton histories. So you're just getting the input-output behavior. And that's convenient if we want to sort of reason about reachability without caring about which paths we have. And I'll write phi of a pol to mean that simple syntactic substitution operation. Okay, just to briefly review, this is the Netcat semantics. And the one thing I'll point out to you is that the dupe operator, which has replaced the link operator, it really just does duplicate the head packet and make the history one element longer. So it's very simple. Okay, so before I can tell you about how to verify properties of networks, I need to tell you how to encode a network into Netcat. And there's really two ways you could do this. So one way is maybe I've convinced you that Netcat's a great language for writing network configurations, and so and you go back to your institutions and convince your network operators to use Netcat, and so maybe you have a model in Netcat already. But I'm sad to say, although we've had a lot of users of our system and technology, we don't yet have sort of thousands of Netcat programmers in the world, and there aren't many networks that are run using Netcat outside of the CS department at Cornell. So that's OK, though. It turns out that netcat's actually expressive enough to encode sort of other lower-level representations of network programs. So if you're an OpenFlow programmer, you can actually take the artifacts that your controller generates and encode those into netcat, and then go off and verify those models. So I'll show you very briefly how this works. So if you think of a sort of low-level implementation in a software-defined network, what it consists of is basically you have all the routing tables that the switches have. And remember, those are just lists of patterns and actions. The patterns have to be positive conjunctions of tests on header fields, and the actions include things like drop, forward a packet out of port, and you can also modify header fields. So it's pretty simple because, remember, we saw that netcat can encode conditionals. And so it's a pretty straightforward translation to just take these tables and turn them into a series of cascaded conditionals. We just take the first rule, put its pattern as the topmost test, and then translate its action into netcat as the first branch, and then we fall through to the second conditional, which has the test for the second rule, and so on. So that's dead simple. And then either directly or by this translation I showed you a couple slides ago, because we can encode the structure of the network itself as a netcat term, we can take the network topology and turn it into a big union of link terms. And we have 2 terms for every physical link, assuming they're bidirectional. So the link between A and B becomes the link from A to B and the link from B to A. OK. And then if we've encoded all of the routing tables on all of the switches, we can build a big term POL that is basically the union of all of those tables. So we take the table for a given switch, prefix it by the test that we're on that switch, and then take the union of all such terms. And we get a single term that represents the local forwarding behavior of each device. And then we can take our encoding of the topology as the big union of links, and then to get a term that encodes the end-to-end behavior of the network, we just close the composition of the policy and the topology under Queenie star. So what this captures is doing nothing, or behaving with the identity, or taking one processing step, which is going across a switch and a link, or 2 steps, or 3 steps, or any number of steps. So this will be our basic network model that we use as a basis for verification, assuming that the program was not written in netcat, but was written using some other tool. OK, so once we have an encoding of a network, we can start asking questions of that encoding. And there's sort of a classic technique that's used in a lot of approaches to verification, which is if you have a formal framework of some sort that can both encode specifications and implementations, then you can start reasoning about how those things are related sort of directly in the framework by checking things like inclusion and equivalence, or inequivalence. So for example, if we have a network and we have some distinguished ingress location and some distinguished egress location, and we want to ask, is the egress reachable from the ingress, then what we can do is take our network model, Paul topo star, and then prefix it by the predicate that describes the ingress and the predicate that describes the egress, and then just ask if that's equivalent to false, if that's inequivalent to false. So if it's not inequivalent to false, then there is some packet that gets from the ingress to the egress through the network in 0 more steps. And if it is equivalent to false, then there's no path.
Why are you posing the question in terms of being not equivalent to false?
So if it is not equivalent to false, then out is reachable from in. So I'm trying to ask, is this thing reachable? And so I have to ask, is it not false?
Oh, wait, no, I see that.
I mean, it's either equivalent to false or not. So we can, we'll check if it's equivalent to false, and we'll either get a yes, no answer.
Sure.
Okay. And there's other sort of simple variations on these kinds of reachability queries you can answer. Here's one that we did in our POPL 14 paper. So one property that network operators often care about is, does traffic go from some ingress to some egress, but maybe through a waypoint? So suppose, for example, your network has a firewall, has a set of firewalls, and they're sort of distributed throughout the network, and you want to make sure that all traffic goes across one firewall before it gets to your precious servers on the inside. But there could be many paths through the network, and some of them don't go through the firewalls. So you could ask, does the network always forward from ingress to egress through a waypoint? And what we can do is ask if, so we again take our network model, slap in and out around it, so that captures the paths that go from ingress to egress. And then we can ask if that's somehow included in all the paths that start at the input and then go through the network without reaching the output, then go through the waypoint, and then go through the network without going back to the input, and then get to the out again. So we can sort of build these little path expressions that capture properties of interest and then check either equivalence or inclusion. And I haven't told you what inclusion is, but you can basically encode inclusion in any cat-based system because we have union. So to ask if P is included in Q, we just ask if you take P and you add Q, is that equivalent to Q? If that's not the case, then somehow P had some stuff that wasn't in Q. OK, so I'll give a few more examples at the end of how we can do various forms of reasoning. But essentially, any property that involves reasoning about forwarding paths can be reduced to something involving equivalence. So that suggests that we should have some techniques for proving equivalence of netcat programs. And I'll show you two different techniques today. One that's based on equational reasoning with a set of axioms, and one that's based on automata theory. So let's start with the equational reasoning. So I already sort of mentioned this, but I wanted to sort of have a slide to really emphasize it. Netcat's design is really not an accident. It's based on this sort of very well-pedigreed, well-studied, elegant system called clean algebra with tests that Dexter Cozen's been working on for several years. And it really kind of has this canonical structure consisting of the regular operators, which you can think of as encoding the paths through the network, and the Boolean operators, which encode basically the switch forwarding tables. And the great thing about netcat being an instance of one of these clean algebra with tests is that cat has a proof system that can show equivalences between arbitrary terms. And as it turns out, netcat has a sort of simple extension of that proof system that also works very well for proving equivalences between terms. And just to throw it at you, here it is. So what you see here is a whole bunch of equational axioms. They're all either of the form P equivalent to Q, or there's a couple involving star that are horn clauses, so they involve implications. And I grouped these into three subgroups. So we have a bunch of axioms that talk about just the clean algebra fragment of the language. We have a bunch that talk about the Boolean algebra fragment of the language. And then we have some axioms that talk about how our packet operations interact with each other. Just to highlight a few of these. Ooh, my animation made it very faint. These axioms capture sort of natural things you'd expect, like concatenation or sequential composition, being associative, distributing over union in the way you'd expect, and then also things like when we have tests and modifications, they sort of act like imperative operations you'd expect in any programming language. So, for example, if I set field f to n and then immediately test if f is n, that's the same as if I just set f to n, because the test becomes redundant once you've done the assignment. Another example, if I do 2 assignments in a row, then the effect of the second is the only one that I need. I could have ignored the first assignment. So the details of these axioms are not super important. If you're familiar with sort of semirings and other algebraic structures, you'll be used to the idea of a system that's characterized by some signature and some equations. That's exactly what this is. The neat thing about this system is that it has the two properties that you want of any proof system, but are, of course, very rare, which is that they're both sound and complete. So soundness just means whenever we can prove that some netcat term is equivalent to some netcat term Q, sorry, I think I screwed that up. If some netcat term P is equivalent to Q, if we can prove that using those axioms, then actually in the unitational semantics, they're actually equal. And completeness just says the opposite. Whenever we have two terms that happen to describe the same function on packet histories, then there's some way to prove that they're equivalent using just these axioms. So I'll prove completeness for you in Sketch in a few slides, but let me first just show you why having these equational axioms is useful. So one application is you could imagine using them in the context of a program optimizer and basically the axioms would serve as little witnesses to the correctness of certain optimizations. So this is a toy example, but I think it illustrates the point. So you can imagine a network with a simple straight line topology. It's got a host connected to a server, and there's two switches A and B in the middle. And the question that I want to answer is, does the network behave the same from an input-output perspective? So again, ignoring dupes, if I put firewalling rules on A or on B. And intuitively, it shouldn't really matter, right? If I'm dropping the packets on A or on B, from the end-to-end perspective, the network only forwards traffic from the host to the server if it gets across a firewall. So formally, we can ask, does this equivalence hold? If I have a routing program that describes the tables on both A and B, and then I have some firewall rules that drop certain packets, is it the case that if I run this union as my pol in that broader construction of pol topo star, do they have the same behavior? And you'll notice that in the first one, I'm doing the firewalling on A, and in the second one, I'm doing the firewalling on B. And I won't step you through all the details because it's a little bit tedious, but you can see our POPL 14 paper for, this is the whole proof except for a couple of lemmas that are a little bit shorter. But essentially, you can systematically rewrite the program that does the firewalling on A into the program that does the firewalling on B using just those axioms, other theorems of clean algebra with tests that have been proven previously, and a couple of supporting lemmas. So you can, and this proof, can be quickly checked. You can just check that each pair of adjacent terms are in fact equated by the axiom that you see in braces, and this would give you a quick way to have confidence that this form of optimization or code motion is correct. All right, so let me now dive in and prove completeness. Completeness, of course, is a property that most logics don't have. Most interesting logics are sufficiently expressive that you basically can't have completeness, completeness. So the idea in the proof of completeness is I'm going to use the netcat axioms to rewrite programs until I just have a regular set of strings. And at that point, there's an existing theorem that Cozen proved in the mid-90s, which shows that just the clean algebra axioms are complete for any regular set. And so sort of all the work is going to be in the pre-processing to sort of massage our netcat terms into this sort of reduced and normal form. So I'll take you through the details for a couple of reasons. It's a little bit hairy, but it will sort of serve as a warm-up for the netcat automata we're going to build later, and it also is used in the compiler that I'll discuss on Monday. Do you have a question or just stretch? Okay. Okay, so the first step that I'm going to do to get towards completeness is to take the surface language and put it into a reduced form. And the main thing I'm going to do is I'm going to replace all of the Boolean predicates with what I'll call complete tests. So for simplicity, I'm just going to consider two fields in this example, switch and port, but you would actually do this for all of the fields that are in a packet. So the idea is a complete test doesn't just test one field. It doesn't contain any unions or negation, but it actually contains a conjunction of tests for every single possible value in the packet. So essentially, the complete tests and packets are in one-to-one correspondence. Every packet has a unique complete test that matches it. And likewise, I'm going to take all my assignments and turn them into complete assignments. So I'm never just going to rewrite some of the bits. I'm going to rewrite all of the bits in the packet. And I'll use alpha to range over complete tests and beta to range over complete assignments. And so I'm going to do a rewriting that takes my surface language and sort of makes all the tests complete tests, all the assignments complete assignments. And what I end up with then is a much smaller language that's just the regular operators plus complete tests, complete assignments, and dupe. And it's not hard to show that, again, using the netcat axioms, for every netcat term p, there is a reduced netcat term p prime such that, and I apologize, this symbol should be the triple bar equivalence we had on the last one. So such that you can prove using the axioms that p equals p prime. And just as an intuition for how the proof of this lemma goes, I mean, basically wherever we have a test, we're going to have to do turn that into a complete test. And so we're going to use the fact that we can always basically, any test and its negation we can introduce. The union of those two things, we do have p or not p basically in a Boolean algebra. So we introduce the test for another field and then we distribute over the union. And so this is sort of going to blow up our term, but this is just in the meta theory, so we're okay with sort of blowing up our terms to simplify the tests and modifications.
You don't have negation anymore, so is there like a finite set of possibilities for all the tests?
That's always the case, actually. Okay. So there's, yeah. So we jump back. Where is that axiom? Having trouble seeing it right now, but there's a finite set of fields, and every field is associated with a finite set of integers. So we don't have real integers; we have 32-bit addresses or things like that. So the sort of the equation could be exponent. Yeah. Okay. So we can rewrite netcat terms into this reduced form. So the first attempt we might take is, we know that if we can get somehow a regular set of structures, then this theorem of Cozen will tell us that the Kleene algebra axioms are complete over it. Unfortunately, if we try the sort of obvious regular interpretation, so basically take this little language and treat each alpha, beta, and dupe as my characters, and then use the completely standard undergrad theory of computation interpretation of those as a regular language, which I've written here. Unfortunately, this interpretation is a little bit too picky. So it distinguishes terms that are in fact equivalent. Or to put it formally, if we have two denotationally equal terms, that does not imply that their regular interpretation as reduced terms are equal. And the way to see this is, here's a simple counterexample. So if I, if I take the alpha that tests for switch 1 and port 1, and I then concatenate that with the alpha that tests of switch 1 and port 2, that is the same as testing for switch 1 port 1 and switch 2 port 1. And essentially, I'm taking two tests and they're contradictory in two different ways. So both of these are equivalent to false. But if I interpret them as strings, this is sort of one string with two characters. I've underlined the characters. This is sort of one string with two characters, and this is another string with two characters, and they're different strings. So these things are denotationally equal, but the regular interpretations are not equal. So somehow we need to do a little more work to put these into a more normal form. So the way we can do that is by being a little bit more careful about sort of normalizing things as we try to massage these terms into a regular language. And the sort of trick is we can build a model where instead of having these sort of arbitrary strings over complete tests and complete assignments and dupe, we'll put them into a more restricted form that I have written at the top. So we're going to always have a complete test at the front of every string in our language. And then we'll have a sequence of complete assignments, which indicated by B, separated by dupes. And I'll call these guarded strings. So for example, this would be one guarded string. Complete test alpha 1, followed by beta 2 through beta n separated by dupes. And the intuition is this kind of models the trajectory that a packet might take through the network. So the alpha captures the initial value of the packet. And then on the first device, the first switch, it gets modified to some beta 2. And then it goes across a link. And then it gets modified on the next device to beta 3, goes across another link, and so on and so forth, all the way through the network. And we can build up, we can interpret our reduced netcat terms to give us one of these sets of guarded strings. And it looks pretty similar to what we saw before, but we're doing a little bit more work to make sure that we always have something in this form. So when we, for example, interpret a complete test, we can't just emit that complete test. We have to stick a complete assignment after it. And so this pi alpha notation means give me the complete assignment that's in correspondence with the complete test. So the assignment that sets the values that were just tested. Similarly, when we have a complete assignment, we're going to prefix that by every possible complete test. Because that's what an assignment does, right? It ignores what's there and just clobbers the values. And so the set of all possible incoming values clobbered with this beta is the guarded string interpretation of that. And I won't go through the details, but you can do similar sort of more complicated constructions so that each of these operators denotes a set of guarded strings. And now we have that property that I said we didn't have before. So if we have two denotationally equivalent terms, then that will be true if and only if the interpretation in this language model gives us equal sets of these guarded strings. So that's nice. This model is actually isomorphic to our standard model in terms of functions. Moreover, there's a way to put terms into a normal form such that we can prove that that the term we had was equivalent to its normal form, and the G interpretation here is actually just the regular language interpretation. In other words, the term in normal form, we could have used the R interpretation from before that didn't do all this extra work, and we would get the same result. So for things in this normal form, G and R give the same answer. Okay, so now to prove completeness, what we do is we start with two terms that we assume are denotationally equal. We reduce them and put them in normal form. And by the theorems that we saw, we know that we can build equational proofs that show that P on the reduced normalized version P hat and Q in the reduced normalized version Q hat are equal. And then by soundness, since our axioms are sound, we know that P hat and Q hat are equivalent to each other. And then because we have the property of this language model that it coincides with our denotational model, G of P hat and G of Q hat are equal. And then appealing to this result of Cosen's that Kleene algebra is complete over any regular language model, we get that we can prove that P hat and Q hat are equal. And then sticking together all these results by transitivity, we get that P and Q are provably equal. Okay, so that's the proof of completeness. And the details are interesting because I think this language model that we developed in the middle is much less compact. So when you translate into the language model, you really blow things up. But it really gets at the essence of what's going on in netcat. We just have some regular structure there, but we've sort of wrapped it up in this notation and given it this interpretation as packet processing functions that appears more powerful, but actually it's just a regular model. All right, so next I want to consider how we might automatically prove that some terms are equivalent. And for this, the equational axioms that we saw are probably not the way to go. I mean, you can imagine trying to do some kind of search or something using the equational axioms. But a much better way is to actually exploit this observation that netcat has this regular structure and build automata for netcat terms, so finite automata for netcat terms, that we can then use standard algorithms to check equivalence on. And in fact, we'll see, this gives us a very practical way to decide equivalence and to check properties of network programs automatically. And it sort of follows the standard stuff that you would have done in undergrad theory of computation, but we need some clever symbolic representations to get good performance. I'm going to do a bit of a segue now. So how many of you have taken theory of computation? Oh, okay. Fewer than I thought. How many of you have seen regular languages before? Okay, good. How many of you have seen derivatives of regular languages before? Okay, about a quarter or a third. Okay, so the way we're going to build these automata is using something called regular expression derivatives, which is a really elegant idea that goes back to the 60s and a little bit before. And it's kind of come out again in recent years. People sort of rediscovered it in the mainstream PL community, and it's over the last few years you've seen sort of lots of papers at POPL, ICFP, PLDI on using derivatives for various things. So I thought I'd briefly review how that works, because if you haven't seen it, it's one of those kind of really cool, simple, elegant things that that's just kind of fun. And it's a really powerful and robust way of building automata from expressions that is often much simpler than using the Thompson's construction and subset construction you might have learned in a standard theory of computation course. And we'll use it in NetCat for that reason. Okay, so just to review, so this is a little bit of a tangent, but we'll go over regular expressions and their derivatives. So the regular expressions are just, you take some finite alphabet, some finite set of characters, you throw in the empty regular expression, written 0, and then close it under union, concatenation, and queenie star. And we can give the semantics as a set of strings. So 0 denotes the empty set, single character denotes a singleton containing just that, a string containing just that character. Union is just the union of the two denotations of the sub-expressions. Concatenation is the concatenation of every string in the first and the second. And star is just iterated concatenation with itself. And just a bit of sugar, sometimes people throw in a special epsilon character or 1 character. I'll just write that as 0 star. You can encode it, so you don't need to have it as a... So there's a notion of the derivative of a language. And you can do it in 2 ways. You can give a semantic definition of what a derivative is, and you can also give a syntactic definition of a derivative. The semantic definition is very simple and straightforward. So we're going to write it as this delta of an R. Sorry, this is actually kind of slightly semantic and syntactic, but what I'm doing here is giving you a semantic definition of the derivative of a regular expression. And so this is just the set of strings that remain after chopping off a C from strings in R. So you consider all the strings that are in the denotation of R, take all the ones that start with a C, the character that we are taking the derivative with respect to, and then we just keep the residual strings that are left. So there's also a syntactic notion of the derivative. I'll use some fancy terms because it's going to correspond to some stuff that comes later. It comes in 2 pieces. So the first piece is what I'm going to call the continuation map. And the idea with the continuation map is we're going to write down a simple inductive definition over the structure of our regular expressions. And on the right-hand side, we're going to get a regular expression whose denotation is the semantic derivative. And then there's a second collection of definitions that I'm going to call the observation map, written with an E. And this is also an inductive definition on the structure of regular expressions. It also gives us a regular expression on the right, but it'll be in a sort of more rigid form. So the intuition is that the D definition captures the semantic derivative, and the E definition gives us something equivalent to 0 if the language that we're taking the observation of does not contain the empty string, and 1 if it does. So let's just step through these definitions. Maybe I'll start with the E because I think that's a little bit simpler, and then we'll build up to D. So again, to say it again, the E map or the observation map if we apply it to some regular expression, it should give us something equivalent to 0 if the regular expression does not contain the empty string, and 1 otherwise. So most of these are pretty straightforward. So if we have 0 or a single character, those things do not contain the empty string. So we just return 0. If we have a union, then, sorry, that bar should not be there. Then it's just the union of the E of R1 and R2. If it's a concatenation, then a concatenation contains the empty string if both R1 and R2 contain the empty string. And so we can just concatenate the E's of those, and we get something that's equivalent either to 0 or 1, precisely when we want. And then the one case that introduces a 1 is star. Every Kleene star contains the empty string, so that returns 1. So now to go up to our syntactic derivative, we can again just go case by case. And remember, what we're trying to do is build up a regular expression that describes all the strings that are left in the input expression after removing a C. So just going case by case, if we start with 0, then 0 certainly doesn't contain C. So there are no strings left after removing a C, and so we just produce 0. If we have a character B, then there's two cases. Either C is equal to B, or C is not equal to B. If C is equal to B, sorry, that should be a 1. Then we're left with a 1 after removing a C. And if C is not equal to B, then we're left with a 0. For union, we need to consider all the strings in R1 union R2 and take a C off of all of those. And so we can just straightforwardly take the C's off the R1s and take the C's off the R2s. The interesting case is for concatenation. So for concatenation, there's essentially two clauses. The first clause is kind of the obvious one. So we need to take a C off of strings that are the concatenation of something in R1 and R2. So we can either take the C off the R1, the strings in R1, and when we're done, we keep everything in R2. Or, if R1 contains the empty string, then we could sort of skip over R1 and take the C from R2. So we get this union of these two cases for the concatenation case. And then the star case is simple. We're going to take a C out of somewhere. It has to come out of R. And after taking a C out of R, we still have all of our star left. OK, so this is the standard definition of a derivative. And you can prove a little lemma showing that E and D have the properties that I said they should. The amazing thing about these derivatives, and the main theorem that the person who introduced them proved, was that up to a fairly coarse equivalence, so associativity, commutativity, and idempotence of operators like union, every regular expression actually has a finite number of derivatives. So if you take a regular expression, remember that our character set is finite. Take all the derivatives with respect to every character. That gives you some finite set of regular expressions. And now do that on all of those and keep going forever. What this theorem says is, at some point, you'll stop. You'll hit you'll sort of run out of new expressions to consider. You do have to work up to equivalence. Just to give you the reason that this theorem isn't trivial, you'll notice that it's not the case that our expressions are getting smaller. So it's not like when we take derivatives, the expressions get smaller. They can get bigger. In both the concatenation and the star case, we actually produce maybe a bigger expression. But as you start normalizing things modulo ACI, you're going to crunch things down. So for example, if this might produce 0, like if R1 does not contain the empty string, this will be 0, and then that would cancel out this, and then we have something plus 0. And so if we were to recognize that equivalence, we would, that term would disappear. OK, and this actually suggests a really simple and straightforward way to build deterministic automata in kind of one step using derivatives. So the idea is that our automata are going to be labeled by regular expressions on the states, and we'll sort of build it iteratively. So if we're building the DFA for an expression R, we'll pick R to be the initial state, and we will, from R, compute all the derivatives for our entire alphabet. And then we get some new states, dA of R, dB of R, dC of R. We'll label a state as being final whenever E holds of it, and will only generate new states for expressions that we've not seen before, modulo ACI. So that theorem that Brzezowski proved, saying that every regular expression is a finite number of derivatives, is what gives us the finite state property of our automata. At some point, we're going to run out of new states to generate, and we'll be done. So the advantages of this approach to building automata is it's very simple. You can show it to any computer scientist, and they'll immediately be able to understand it. The proofs of correctness are very simple and short. And it's kind of very robust. So as you start adding stuff to regular expressions, like you start adding maybe negative operators like negation, intersection, shuffle closure, other complicated operators, it's easier to extend this construction, in my opinion, than to sort of apply the classic Thompson construction and then the subset construction and so on. It's also easy to make lazy. So you sort of get these nice runtime representations of the sort of intermediate construction of an automaton. And so DFAs can be exponentially larger than the corresponding NFA, but you can often get away by not building the whole DFA and just sort of unfolding it as you go. So the representations here are simple enough that that kind of optimization is easy. And one other thing that's very important in practice is I claim that these automata are finite because of that theorem of Brzezowski. The theorem of Brzezowski is sort of the minimal set of the minimal equivalence that you need to have to get termination of this algorithm. But of course, if you want to try to recognize more equivalences, then at the cost of maybe maintaining slightly more structured representations or doing more work to check equivalences as you build the automata, you can get smaller automata. And if you take this all the way to the limit, like you work up to language equivalence. So you assume you have some oracle that will tell you if two regular expressions are equivalent, and you only generate a new state if it's truly different semantically than some other expression than all other expressions that you've seen before, then you actually get the minimal automaton. So it's kind of easy to dial up and down sort of the amount of optimization you do. Is there a question?
Yeah. So on the same page here, this new automaton you're building recognizes this original language, but it's easier to work with?
So yes. And I don't know if I can quite say it's easier to work with, but it's a direct way to get a DFA. And it's, I would argue, simpler to add features to regular languages and build DFAs for those extensions than if you do things the kind of traditional textbook way.
So this is the way of constructing
DFAs.
from an expression?
Yep.
Okay.
Yep.
And it's more compact than traditional construction?
Yeah, so if you have an extension, all you need to do is extend the notion of observation and continuation, prove your theorems for those new cases, and then apply this construction, and you still get a DFA. And in fact, as I said, DFAs can be exponentially larger than NFAs, but you can also build NFAs using variants. So there's something called the Antimirov derivative that gives you NFAs instead. Okay, so next I want to try to apply this to netcat. And to do that, I'm going to show you first, we're going to build slightly different kinds of automata. They'll be hopefully familiar and very similar to standard finite state automata, but again, we're going to work with packets and so on, so they'll be slightly different. So first, to define what a netcat automaton is, it's just a four tuple where I have a finite set of states S, a start state S naught, S0, and two functions. And here's where the difference comes in. So instead of just having final states and a transition function, the analog of the final state is going to be a function epsilon that captures what happens at the last switch. So at the last switch, you essentially have a local netcat program. So you have something that implements a function from packets to sets of packets. And that's exactly what epsilon does. So in a given state, we can sort of be done by taking some input packet and producing a set of packets as output. So that's kind of the observation function that we had before. And then the transition function takes some input packet, that's kind of the characters that we're consuming, and then it transitions us to a set of new states, sorry, that should just be S, and packets. So basically, what the continuation function captures is from the input packet, we did some processing up to the next dupe, and then we transitioned to another state, which is captured here. So I think the next definition will illustrate this. So the input strings to this automaton are structures like this. So we have the input packet and the output packet, and then we have a possibly empty sequence of packets separated by dupes. So we always have the input and the output, but then we might have some additional stuff in the middle. And we can define a notion of acceptance for these automata by a simple definition. So a netcat automaton M accepts an input string from state F, either by, so if we're in S and we have the equivalent of the empty string, so just an input packet and an output packet with no dupes in the middle, then the output packet needs to be in the set produced by epsilon from S on packet in. But my autocorrect changed it to pat. And then the other case is if I have a string that contains a dupe. So it starts with packet in, it has some first packet, and then it has a dupe, and then it has the rest of the string. Then I need to find some state S prime in delta of S on my input packet that's associated with packet 1, the second packet. So I sort of match the first input and intermediate packet that I got using delta. And then I have to go accept from S prime that intermediate state packet 1 as the new head packet and W. So I've sort of consumed everything that happened up to the dupe. I chop it off, and then the packet 1 sort of gets copied over because that head value gets carried over, and then I keep going. Okay, so this is a little bit maybe non-standard and mysterious, but and I don't have time to dwell on it too much longer, but if you look at this again, you can sort of, the intuition that I like is we have these trajectories of packets going through the network, and these automata are basically matching those trajectories by using delta to chop off sort of pairs of inputs and outputs up to a dupe, and then at the very end, we use epsilon to kind of emit the final packet. Okay, so just like in the regular expression case, we can build syntactic derivatives and use that to build netcat automata via some pretty straightforward inductive definitions. So the way this is going to work is I'm going to start by labeling my netcat term by associating a unique label with every occurrence of a dupe. So take my term, there's some finite number of dupes, and just label them with some set of labels L. And the intuition here is that those dupes are going to correspond to the state of the states of the automaton I'm going to build. So the types of my observation and continuation functions done syntactically are, if I feed in a policy, I'll represent my observation function just as a local netcat program. So it'll be a program without dupes. And then for the continuation map, I'll represent it as a set of triples containing a policy that describes the local behavior up to the dupe, the label of the dupe that I encountered, and then the rest of the policy that I have after that dupe. Okay, so let me show you the observation map. So remember, the observation map is supposed to capture the input-output behavior, or the equivalent of that small epsilon, with no dupes. And I'm going to encode that function using local netcat terms. So there's a whole bunch of cases that are false. So basically, everything involving predicates, modifications, or dupe are just false. And then the interesting cases are for union and concatenation. It just follows like I had for standard regular expressions. And then for star, I just take the program and pull the star to the outside. The interesting case is the continuation map. So remember, this gives us this set of triples, the local program up to the dupe, the label of the dupe, and then the continuation that follows. So again, any term that doesn't contain dupe is just going to give me the empty set, because there's no dupe that I encounter, so I can't possibly do processing up to a dupe. the interesting case is for dupe. So if I have a dupe labeled by L, then the processing that happens before that dupe is just nothing, or the identity function, which is true in netcat. Then I have L, the label on that dupe, and then the rest of the program is again the identity function or true. And then the rest of these definitions look very much like what we saw for the standard regular language case. So for union, we just take the union of the two Ds of the two policies. For concatenation, we can either go up to the dupe in pol 1, or we can do the processing not including dupes in pol 1 and then find the dupe in pol 2. And then for star, it's a little more complicated, but essentially we do any processing not involving a dupe in pol star, and then we find the dupe in pol, and then we still have pol star left. Okay, so this is probably a little thick if you're not sort of fluent in derivatives, but I guess if you're not, then the key takeaway is that sort of with a somewhat more complicated generalization of derivatives, we can define the same notion for netcat terms. And, oh.
It looks like on your observation function, you can't get any.
Yeah, I noticed there's another typo there. So, yeah, these should all be the identity. So false should be false, true should be true, test should be test. Yeah, sorry, I'll fix that when I post it. Thanks for catching that. Okay, and just like for regular expression derivatives, you can show there's a finite number of derivatives modulo ACI. Okay, so now we can build some automata that I'll call the program automata using these derivatives. And to do this, I need a little bit of notation. So essentially, I need a way to go from the label of a dupe and figure out what is the continuation or the rest of the program that occurs after that dupe. So there's a nice lemma you can prove by induction over these definitions, which is that for every label that occurs in a netcat program, pol, there are unique programs D and K such that D, L, and K are in the continuation map of pol. And I'm just going to write K sub L for that unique continuation. So you can think of it as sort of a global lookup table that for each label L gives me the continuation associated with that L. So now I can build a program automaton for M by taking the set of states to be the set of labels that occur in the pol plus one initial label 0. I'll let 0 be the start state. And then I just build up E and delta sort of using the semantic properties of the observation and continuation functions. So for the observation function applied from a state L in a packet, I'm just going to get all of the packets, packet prime, that you get by running the continuation map of of L, and taking its observation map and then the denotation of that on the input packet. And the continuation map is similar. So this tells us how we can build finite automata that are equivalent to our netcat programs that we started with. So now we can decide if two programs are equivalent by using these automata representations. And we can basically use a standard algorithm. I'm calling it by simulation, but it's basically just checking equivalence of the two automata that I built. And the core part of the algorithm is basically a procedure that checks if from two states that we need to be equivalent for the overall automata to be equivalent, can we distinguish them locally here? And if not, then we take all the derivatives and all of those have to be, all pairs of related states have to be equivalent. So to step through this in a little more detail, if I'm given two states S and S prime in automata M and M prime that I want to be equivalent, so the initial call would be for S0 and S0 prime, then if I can distinguish their observation functions, then I immediately return false because they do something different at the very beginning. And otherwise, I consider all packet and packet prime such that if I run the same input packet through delta in the two machines, and I consider all the packet primes that come out and then all the states associated with those, I recursively check all those pairs of states. And if all of those return true, and when I've exhausted every possible pair of such states, then I can return true. So this algorithm is pretty straightforward. Of course, to actually make this practical, you'll notice that here I formulated it in terms of sort of enumerating through every possible packet. And you wouldn't want to do that. So to make this practical, you need to find some symbolic ways of only testing sort of representatives from sort of large equivalence classes of packets. And there's some tricks you can use in implementation to make that practical. Just to show you one more example of how you can reason about networks using this technology, one thing that we were sort of pleasantly surprised by is once you have this automata representation of a program, you can actually use it to check some additional properties for which it's not obvious how to reduce them to equivalence. So one of them is loop freedom. So I said at the beginning, loop freedom is one of those properties that you always want of a network. You never want to have forwarding loops. And the previous tools that people have built for checking static configurations have checked loop freedom by essentially enumerating through every possible location in the network and then running some set of reachability tests from there to see if there's a loop. Using these representations, we can more or less check it directly. So the idea is that if the network has a loop, then there's some packet alpha such that from the ingress to the network, going through our model, we can get alpha and then go through the network again and get alpha again. So if this is somehow, if it's possible to do this, then we have a loop. And we can do this by using our automata representations. So if we want to find which alpha might be participating in a loop, then we can consider all packet and packet primes such that for some input packet, going through the phi of our ingress predicate and our network model, we find some packet prime. So this basically sort of computes the intermediate packet in the middle of the network that might participate in a loop. And then see if, when we run the packet through this term, pt star, if we can sort of go from packet prime back to packet prime. Sorry, I'm noticing this should be a plus instead of a star. We need to go through at least once, otherwise that's always true. Okay, so in this way, and again, there are some ways of doing symbolic representations of sets of packets that let us actually check these kinds of properties quite efficiently in practice and faster than somehow enumerating through every possible port in the network. Okay, so let me tell you briefly about some implementation highlights. So I've alluded to the fact several times that in order to make these algorithms practical, you can't work on things like complete tests and complete assignments or raw packets. You need to somehow, find coarse equivalences and sort of work with symbolic representations that reduce the sort of space you have to explore. So you can see our POPL 15 paper where we describe some data structures. We call them bases that encode sets of complete tests and assignments, and something called spines that encodes the set of terms that are manipulated internally when we take derivatives and build automata, and then actually a sparse matrix representation of the E functions that we can build and check properties of very quickly. And we sort of threw all our sort of favorite implementation hacks at making our code fast, including using smart constructors to normalize data structures, so we sort of recognize lots of equivalences. We used hash consing, so there's only one representation of each unique syntactic term. We use memoization in places, so we avoid computing the same answer multiple times. We have some heuristic compaction algorithms that sort of take loose representations of sets of packets and turn them into more compact representations. We use standard fast multiplication tricks for matrices. We also use some tricks for computing fixed points quickly. Just to go back quickly, almost all of our algorithms involve building somehow the network model, and that always involves a clean star. And there's sort of naive ways to construct that fixed point, like start from the identity and repeatedly multiply in pt star. But there's other techniques you can use, like you can use squaring, or there's even some rewritings you can do to, when your program, for example, starts with a predicate, you can exploit that to thin out the size of the intermediate structures that you have. And we also use the union find data structure in our bisimulation procedure. So all of this together sort of tries to sort of prune down the set of intermediate data structures you have to represent as you build the automata representation and then check them for equivalence. So to try this out, we ran a bunch of experiments on some standard benchmarks. So we took some real-world topologies. Fortunately, there's a lot of topologies that have been published sort of in the public domain. So we took the topology zoo data set, which is a large data set of, I think, 250 some odd, mostly ISP and backbone topologies. We took fat tree topologies, which are commonly used in data centers. And the nice thing about fat trees is you can sort of scale them up from a small number of nodes up to many thousands of nodes. And then we also took the Stanford campus backbone, which some researchers there have been nice enough to put on GitHub. We then had to build some configurations for these networks in order to do verification. And here, unfortunately, there are not very many open data sets. So what we did is we built some simple policy generators that did things like compute the shortest path forwarding expressed as open flow tables for an arbitrary topology. We were able to get the production policy for Stanford's backbone because they've released that. And then we asked a bunch of verification questions. So we asked questions like point-to-point reachability between specified ingresses and egresses. We also did all pairs connectivity, where you ask, can every host talk to every other host? We did this loop freedom property that I talked about. And we also did runtime validation of the netcat compiler. So we took these large policies that were describing shortest path forwarding or the Stanford configuration, and we ran them through the netcat compiler and then checked if the output of the compiler was equivalent to the representation that we'd fed in as input. And the results are essentially that our tool is competitive with other state-of-the-art tools, although it's based on this slightly more mathematical and canonical structure. So I have just briefly some summaries of sort of the performance. You'll see that, so note that this is a log graph, so it's things are growing very quickly. And I should say the decision procedure for netcat is p-space complete, so we can't hope to somehow get an efficient algorithm for all possible inputs. At some point, it's going to spike up. But the thing to notice is sort of up to policies that are sort of in the 100,000 ballpark, we can do verification of things like all pairs connectivity in sort of tens of minutes or low number of hours. Similarly for things like loop freedom, and translation validation is a little bit more expensive, but that also does complete eventually. And I guess the other point I want to draw your attention to, so we also did some scalability experiments on the fat tree, and we looked at the relative costs of verifying connectivity versus loop freedom versus translation validation. The other thing we were quite pleased by is we were able to get sort of verification of point-to-point reachability down to well under a second for the production configuration that's used in Stanford's backbone. And at the time, it was about an order of magnitude faster than the numbers that have been published for a competing tool. Since then, they've tuned their performance so they're in the same ballpark as us. But there's sort of a whole bunch of fun you can have putting in little optimizations into these tools to identify fast paths that sort of match up with some of the idioms that are used to construct configurations. In the case of netcat, all of these optimizations were actually based on the netcat axioms. So where we were sort of pruning off a path that we knew was hopeless, often that pruning corresponded to one of the netcat axioms that told us that there was some equivalence with false. So unlike other potentially more ad hoc optimizations, these were all based on a standard theory. Okay, so just to wrap up, there's a lot of interest in the SIGCOMM and NSTI community in network verification right now. So I was talking to some of you around lunch. If you're interested in verification and synthesis, this is a domain where there are lots of real-world problems and a lot of energy at the moment. Netcat can serve both as a formal reasoning framework as well as a programming language. So I think the way the language sort of works equally well in these two roles is quite nice and elegant. And if you learn nothing else, I hope you appreciate that regular expression derivatives are a really simple, elegant technique for building automata from expressions that have been really fruitful for several decades and beyond. And then lastly, with a lot of engineering, you can build practical verification tools for networks that scale up to handle real-world topologies and policies. As reading, the material from today comes from a pair of papers, one that was at POPL 15 and then one that was at ICFP 15. So this paper describes the automata representation and decision procedure for netcat. If you're interested in things like coalgebras, it's a wonderful read. If you're more interested in sort of the concrete automata representations, it's a little bit abstract. So if you want a more direct representation, or a more direct, rather, description of how to build these automata, the middle section of this second paper gives a more sort of concrete definition. Just again to acknowledge collaborators, this was work done with a bunch of folks from the netcat team, in particular Arjun Guha, who's at UMass, Dexter, of course, Matt Milano, and Lori Thompson were the main people behind the decision procedure, and then Alessandro Silva and Spiros as well. All right, so thank you, and on Monday we'll talk about compilation and dynamic updates. Thanks.